want the terminal velocity, and terminal velocity is reached when these two forces are equal. So it will be reached when mg sine theta is equal to ILB cosine theta, right? But what is I? We need to find what is I, the current. So to find the current, we need to know what is E, the EMF. The EMF for this case is d phi b over dt. Negative sign doesn't hurt here. So it is decreasing. Why it is decreasing? Because the area is decreasing, right? This area is decreasing. But notice that magnetic field is not actually perpendicular to that area. There is a angle in between, right? So the change per unit time in the area is going to be L times V, right? So we are going to get B times L times V, but there will be this angle for the change, cosine theta. All right, the current is E over R, which means that the current is BLV cosine theta over R.
So why did we take cosine?
Because this is the area vector,
Yes.
and in between they have theta.
Theta isn't the other.
Look, this is theta, this is area vector, this is magnetic field, right?
Okay.
So this is theta, this is theta. Thank you. So then I have mg sine theta equals to, yes, b squared L squared cosine squared theta times V over R. Is that correct? So terminal velocity, this is the terminal velocity. Terminal velocity is this expression. B squared L squared cosine squared theta. That's it. Okay? As you can see, sometimes the questions are very short, sometimes they are long, and this question is not finished yet. Okay? What?
Plus the work that gravity has done and the heat dissipated by the particle.
Yes, yes.
Not at all.
Yes, very good. What is the instantaneous power dissipated by the resistance R at terminal speed? Instantaneous power dissipated by the resistance. Okay. Exactly. P is I squared R, and we know what I is, right? So we can just write it as B squared L squared V squared cosine squared theta over R squared times R. But then we need to put in here the terminal velocity expression.
So it's easier to multiply I and V.
It's easier to?
Multiply I and V. Not
Is
I
it-
squared R. If it's
Okay, okay,
You can
okay, but yes, eventually you get this, right? Good, no problem. But we need to put in Vt squared, and it's just some expression like B squared L squared cosine squared theta over R times M squared G squared R squared sine squared theta over, I feel like I'm. Is this correct? It seems to be correct because I'm also checking from here. So we get m squared g squared over b squared l squared r tangent square theta. Okay?
Correct.
So far so good? Did you follow this? All right. What is the speed of the rod as a function of time? As a function of time. So,
But in that case, we found the instantaneous powers.
mhm. Yes, what's the question?
This was not
Hocam, can we find this from double derivative of the energy? I mean, we know the potential energy change, mgh.
Um,
nasıl double derivative?
so, you are asking whether we can find it from change in the potential energy, right? It will be quite tricky, but yes, not impossible. Okay. Then final question is, what is the speed of the rod as a function of time? And what is done here is we just write the equation of motion for this system, which is, so let me, this was part C. So for part D, I'm going to just write F equals to ma. So m times a is this. Do you agree with this? F that is pulling down is mg sine theta. Do you agree with this? And the thing going against it was ILB cos theta, right? And I was BLV cos something. So I have basically b squared L squared cos squared theta over r times v. Is this something that you can solve? Right? First order equation. And if you solve it, you will get something like this. Let me just write down the solution. It's v terminal 1 minus e to the minus t over tau, where tau turns out to be mr over b squared L squared cosine theta. Okay? Do you have any questions?
Hocam boundary'lerde sıfırdan V'ye, sıfırdan T'ye olacak.
Yes. With putting v prime and t prime. Yes. So the next question is, it involves change in magnetic field and it should be solvable, right? I'm trying to figure out whether it includes chapter 31 or not. So just give me a time. Assume that the magnetic field has been oscillating for a long time so that AC steady state is reached. So out of question, right? Switching, skipping that one. Skipping this one as well.
Diğer hocanın ismi Sibel dedi. Opsin demedir.
We are recording.
Hocam,
Yes.
our math teacher does something like this old exam questions that are in the, like, we are covering that part. Okan Tekman does that. It's really useful because sometimes, right now, I don't know which exam topic is like, which final are covering our final exam. Did you understand what I'm saying?
I
Can
think
you make a list like that? Like just from one of, like one of the...
the short answer is I can't. I don't know the questions.
No, not like that.
Uh,
I can say.
the position and the velocity of a particle with positive charge q and mass m at time t equals to 0 is given by r equals to 0 and v is vk. So r at time 0 is 0 and v at time 0 is v0k unit vector. The particle is moving in a region where uniform magnetic field B exists, and it's B equals to Bxi plus Byj. Okay. Find the magnitude of the acceleration of the particle in the region. Magnitude of the acceleration. Do you understand the question?
F equals Q equals P equals 7.
Exactly. F equals QV cross B, which equals to MA, and we need absolute value of A, magnitude of A. All right. So we are dealing with Q times V0K and then cross product Bxi plus Byj, right, is equal to MA. So A is equal to QV0 over M. What is K cross I? Is it J? J. What is, I need Bx, right? Bx, J, and K cross J minus I, very good. So By times I. Do you have anything to add to this? No. So what is the absolute value of A? How do you find it?
I take this square root of Bx squared plus By squared.
That's right. This is the absolute value of the acceleration. Does it make sense to you?
In mathematics class today, we talked about this, how calling it the absolute value of A would be wrong, but people would still understand it. It should be called the magnitude.
The magnitude. It should be called the magnitude. I agree. What will be the maximum z coordinate of the particle during its motion? Do you understand the question?
At first it's at the origin.
Yes, at first it's at the origin. What will be the maximum z coordinate of the particle during its motion?
Let's draw the circle.
Let's draw the circle. So this is x, y, z, and there is a magnetic field pointing in this direction somewhere, right? And the particle starts moving in this direction. No. Magnetic field is in this direction. Do you agree? So they are 90 degrees. With respect to each other. So what kind of motion do you expect from this particle? Circular uniform motion. What will be the maximum z coordinate?
Maximum minimum sorusu aslında.
So
Solve it that way, that's
wouldn't it be the radius of the circle? It's
Yes,
very
but
hard.
At one point, yes, it will be.
It will be the radius, right? Because it will just go out like this and go back and come back. But I couldn't draw it properly because it's
Its motion in which plane? I mean,
a very good point. Its motion is in x equals to y plane. Its motion is going to be,
John, we are not sure if Bx is equal to By though.
yes, that's right.
It will be what y equals mx, but we cannot be sure of m as long as we don't know the values of Bx and By.
Yes. Which way will it go? So let me try drawing it like this. Okay, it starts like this. The magnetic field is in this direction, and it will go which way? If the charge is positive, V cross B is pointing this way, right? Did you follow so far? So it will make a circle in that direction. Do you see what I mean? It will rotate like so. Okay, and the maximum will be when it's R. Okay, and we need to just find R. Do you remember the expression for R? mv over qb. Yes? qb. What is v? v0. What is b? b is bx squared plus by squared square root. Right? Everybody agrees with this? So z max will be this value r. I hope you did understand what's going on.
You couldn't draw very well.
No one can. Right? Very hard to draw it.
Actually, perhaps we could. Yes.
If you draw the plane first and you can draw circles on it.
Okay, let me try doing it. So there is a plane that is perpendicular to this green line. I think I'm making things worse.
It's like
There's a plane like this. Is it better? And then there is circle on that plane.
I think it's
As good as it gets. All right.
when we cannot imagine this motion, so since it asks the maximum,
Yeah. It asks maximum, you give the maximum.
It could be
I mean,
trick question.
the whole point here is to figure out that the maximum will be the radius.
I will
R and then
Yes, of course. What is the power supplied by the magnetic field to the particle? It's a 5-point question. What is the power, are you following? Power supplied by the magnetic field to the particle. Any ideas?
I mean 0.
0. Yes, I should have used you.
What dW over dt.
Yes, the thing is that
It would be
it's a circular motion. Force is always perpendicular to the motion. So the powers supplied by magnetic field is 0. The work done by the magnetic field is 0.
power is equal to F dot E, V, and V and F
Yes,
are
that's another way of thinking about it. It's that's how they wrote it. So F is Q V cross B power is F dot V, and since this has to be perpendicular to V, something perpendicular to V, dot product V is 0.
Hocam,
Yes.
can we consider power as a derivative of energy?
Yes.
So there is a circular energy. I mean,
Yes. NV squared over 2.
so
Yeah, and it's not
power-
changing.
Okay. Thank you.
Okay. No, thank you. You also. That's another way of solving it. Yes. Okay. There is a mutual inductance question that is not that interesting, so let's skip it.
Why is it not interesting?
Huh?
Why is it not interesting?
The fact that it's not interesting is not interesting as well. So let's skip it. It's because we have done it before. It's just one coil around the other coil, and you know how to find the mutual inductance, right?
Is it in scope?
Yes. You want me to do it?
No, I just want, isn't it?
Yes.
31 take chapter?
Third, no. Third.
No, it's chapter 30. Okay, yet another this FB kind of question coming. So a particle with charge Q is moving in a uniform magnetic field, and the field is like so. The magnetic force on the particle is measured to be Fxi plus Fyj. Calculate the velocity components of the particle that you can from this information. Do you understand the question?
What is the question?
Calculate the velocity components of the particle that you can calculate. Okay? So there are velocity components that you cannot calculate. Which are they?
Cross product, if cross product is 0, then we can.
Exactly. So the velocity component that is aligned with the magnetic field can be anything. Right? Because that part doesn't produce any force. So let's figure out, let's give it some values. Let's say V is Vxi, Vyj, Vzk. That's the one that we are not going to find, Vz. Okay? Then we can just say that Fxi plus Fyj is equal to Q Vxi plus Vyj plus Vzk cross product Bk. Okay? Then what we have, I cross K is J, so we have Q Vx B J.
Yo, minus, minus 3.
I cross K is minus J. Okay. I trust you. J cross K is plus I. So Vy B I. And K cross K is 0. So that's why we don't have K component. Okay. So Fx is equal to minus Q Vxb, which tells you that Vx is minus Fx over Qb. Do you see? Fy is Qvyb. We are basically matching the same values here. Hence, Vy is Fy over Qb. Did you follow? Yes, good. Are there components of the velocity that are not determined by the measurement of the force? Explain.
Can you repeat the question?
Are there components of the velocity that are not determined by the measurement of force? Explain. It just asks what I have already explained. You cannot find Vz because it's aligned with magnetic field, and it can be anything. It won't affect the force, measured force.
So
Yes.
why did we choose fx, the quantity in front of the j?
Very good. Because this is also J.
Dur, hata yapmış olabiliriz.
Didn't we make it?
Yani evet.
Yes, we made a mistake. We made a mistake. Very good. So we should have chosen this one with this one, and this one,
Only
this
the
one.
subscript will change for the forces.
Only the subscripts will change, yes. So negative remains there, this becomes y, this becomes x. Thank you. So finally, find the angle between B and F. B, Bursa, and F. All right. Let's find it. What is B dot F? Should be 0. Let's confirm that it's 0.
It is 90 degrees.
Yes, it is 90 degrees. B time dot product. So you just have fxi plus fyj. We don't even need to do this, but anyways, you can even see that it's one of them is in k, the other one is in I and j. And in general, this is always the case. Force is perpendicular to both velocity and magnetic field, right?
That's why it doesn't work.
Let's do also v dot f, although it's not asking for that. What is v dot f? Let's figure it out. Minus fy over qb I plus fx over qbj dot product with fx I plus fyj.
The problem is that we do not know the z component of v. We are not going to be able to determine the angle between them.
We are.
Actually,
No matter what Vz is, let's put Vz as well. Vz times k.
we should.
K, there is no k. K dot I, k dot j will give you 0. So as a result, you get negative of fx fy over qb plus fx fy over qb, which is 0. So just remember, v dot f is 0, b dot f is 0 in this situations. It's always the case. Okay, because you are doing this, so it has to be the case. How are we doing so far? Not bad, I guess. Okay. We have done this before. Should I solve this or not?
Even if we have done it before.
Hmm?
it's a waste of time.
Okay, we didn't do exactly this one, so maybe there's a point of doing it. So let me do it. I think we didn't do exactly this problem, so let me do it. So I have a magnetic field pointing in, but the magnetic field ends at a certain point. So it's in, but here the magnetic field is 0. Okay? Then I have a loop like this, and the length of the loop is L. The distance over here is d, and I'm pulling it with an external force. And the force is constant. Okay, the force is constant. Find the speed of the loop as a function of time before it leaves the magnetic field. Do you understand the question? The resistance of this is R and the mass is M. Yes? Okay. So what is the induced EMF here? It's BVL, right? Don't write it like that immediately, but we have done it too many times now. It's BV times D. But if you can write it, please write it. Like if you can't derive but still can write it, that's also fine. So this is the EMF. Then current is BVD over D
Are we sure it is
over
not
R.
2 BVD?
Yes, we are sure. Why should be 2?
I don't know.
Hmm?
Normally, in a question like this, I would solve the loop integral of V cross B dot L.
But this part is outside the
This
magnetic
part is
field.
outside, you're right.
And if it was inside, then there would be no force acting on this because the EMFs would cancel out.
Yes.
All right. So far, so good. Do you have any question? Good. So I have I have F. I don't have F. Let's write down F. F is B times I times D, which gives me B squared D squared V over R. Right? But this F is pointing in the negative direction. Right? What do I mean by that? So there is a magnetic field. In general, all these F's are always against. You have figured it out by now, right? But each time maybe you can analyze why that is the case. So I have a magnetic field pointing in and the flux is pointing in, but flux is decreasing as I pull it out. Flux is decreasing, so the effect is outwards, right? Now, the response must be inwards, which corresponds to a current that goes like this. When you have a current like that, magnetic field pointing in, I cross B gives you a force in the opposite direction. But remember that we also have external force. So the whole thing will have this Newton equation, m dv over dt is equal to F external minus B squared D squared V over R. That is the part that I didn't solve before. Before we just had this part and there was an initial velocity. This time we have an external force. Okay, so the question is just a little bit different. Okay, I will write the end result because we have done this too many times. The end result is this. V of t is going to be F external times R over B squared D squared 1 minus e to the minus B squared D squared over MR times T. All right? Any questions?
Isn't it going with constant velocity?
No.
Didn't you say in the beginning of the question?
No.
How?
I said that the force was constant. Again, it asks for dissipation, force applied. In the limit of terminal speed, they are equal to each other. So, okay, let me see. Should we continue with this question? Yes? You are interested, okay. Find the power dissipated in the loop as a function of time before it leaves the magnetic field. Power dissipated. Okay, let's find power dissipated. So this is part B. Power dissipated is what? I times V, which is I times, well, I can write just I squared R, right? Let me go with I squared R, which is B squared V squared D squared over R. So far, so good. So dissipated power is
Dissipated power nasıl oluyor? Power instantaneous bir şey değil mi?
what do you mean?
It is instantaneous. You found the power. Is it just asking that?
It's asking for find the power dissipated in the loop as a function of time. So power dissipated is,
Well, we already found V as a function of T.
so
We can insert V in the power equation, can't we?
no, that's the power supplied. That's the point. So you want F times V, right? Do you want that? F times V?
No, I mean, in the power equation, we have V squared, D squared over R. Don't we know the function V as a function of time?
Yes, I'm inserting that.
Come on.
B squared D squared over R times, I'm confused a little bit, F external squared R squared over B to the 4 D to the 4 1 minus E to the minus B squared D squared T over MR squared, right? So,
Nasıl buldunuz bunu?
so this is just V squared and I insert V from here. Okay? I hope you are following. F external squared R over B squared D squared times whatever this is. Okay.
Because it asks function of time, we did that, right?
Yes.
It asks power dissipation, I don't know, to infinity maybe. We should take the integral then.
If it asks the total energy dissipated,
Yes.
then you should integrate, yes.
Hocam, can you explain the difference between power dissipated and power supplied?
Of course. Power dissipated is the power that you lose in the circuit. Okay, because of the friction, the power that you lose to the
Sure.
to the resistance. So you are pulling it, okay? Not all of your pulling accelerates the object. Some of it is lost
I see.
to the heat. Not all of your mechanical energy turns into the mechanical energy of the loop. Okay, some of it is turned into heat. Yes, tell me.
That's what I was asking.
Yeah. Exactly. So now let's look at power supplied. So to find power supplied, this is power dissipated. Power supplied is F external times V. Okay. So I have an expression for V, F external squared R over B squared D squared 1 minus E minus B squared D squared T over MR. But this time I don't have the square on top of it. Do you see it? So power supplied is this expression that has the same coefficient in front, but the parenthesis doesn't have a square in it. The other one has a square in it. So as time goes to infinity, what happens to those expressions? What happens to this? 1. What happens to this? Also 1. So, and as t goes to infinity, this supplied power equals to dissipated power, all right? And at that point, the object reaches the terminal velocity, okay? So all new supplied power goes to dissipation. It doesn't turn into mechanical energy of the loop, okay? Have we learned some physics from this as well? Okay.
Hocam, can we consider f in that, I mean yani akımdan dolayı oluşan bir f'imiz var ya hocam.
Mm-hmm.
Onunla v'yi çarpıp p dissipate diyebilir miyiz ona?
That's a good point. Yes, you can.
O zaman yani f eksiyon çarpı v'de k'nin farkını alırsak işte f induction çarpı v.
Yes, exactly. So you can find the surplus of power by finding the total force times the velocity. All right? Very good.
The question could also ask us to find the what? Change in kinetic energy or instantaneous change in kinetic energy.
Yeah, very good. Let's have another break now.